The atoms in this gold ring began their journey 10 billion years ago, forged in violent collisions of stars. This ring is more than a metal. It's the product of cosmic chaos, an incredible story of near impossibility. To create this one ring, the universe itself had to be born. Just a few kilometres from where I'm standing here in Saxony, at the tomb of the dolmen of the goddess, back in 1999, illegal metal detectorists unearthed treasure, gold, the Nabra sky disk. It was made 3,800 years ago, and the first representations of the heavens in artwork. But gold did not just inspire craftsmen, it was traded as it is today. The gold and tin in this disk was mined in Cornwall. As for the modern treasure hunters, they were caught alongside the artifact in 2002. Gold, along with copper and possibly lead, was one of the first metals humans learned to smelt around 6,000 to 7,000 years ago. But gold was different. It was found in its pure form, as flecks or nuggets, unlike other metals. It resists corrosion, making it virtually eternal, and thanks to its unique properties, it can be cold welded simply by hammering. Its atomic structure forms a ductile matrix of atoms, allowing it to be fashioned into incredibly thin sheets or drawn into long wires, like the torques from the European Iron Age. Its rarity and beauty made gold a symbol of power and wealth, inspiring legends and driving men to greed and madness. Even today, gold is everywhere, from jewellery to food wrappers. Between 2,000 and 3,000 years ago, someone walked along this stretch of the little river Gothy in South Wales, perhaps whilst fishing or tending their cattle. In a fleeting moment, they noticed a flash, a golden light in the water. It may have just been a flake, or if they were truly fortunate, a gold nugget. The river had carved into a rare seam of gold ore, and the heavy particles, too dense to travel far, settled in the crevices of the riverbed. Over time, these gold particles collected in the rough river floors, nooks and crannies, cold welding into larger nuggets. Now, these early prospectors scoured the riverbed. They would have realized that the gold finds ended at a certain point, leading them to the muddle lode hidden in the mountain, a seam of smoky quartz rich with gold. Gold, though rare in the British Isles, has been known and exploited for thousands of years. It was used for creating beautiful jewellery and decorations like the famous gold cape of Mauve from North Wales, dating back 4,500 years. Bronze or Iron Age locals would have recognised the gleaming gold within the ore, and understanding its value and potential. For Egyptians, gold was the physical embodiment of Ra, the sun god, while the Mayans believed it to be the sweat of the sun. Gold has touched every aspect of human life, human expression, and even the languages of the world. The story of gold spans billions of years and vast distances across the universe. Something as simple as a gold ring carries within it the tale of our solar system's creation, Earth's geology, and humanity's relentless pursuit of this extraordinary metal. One of the remarkable properties of gold is that it naturally occurs in a native form as a pure metal. This sets it apart from metals like iron, copper and lead, which are often bound to other elements such as sulfur, and require skilled smelting to extract. The local quartz at Geological also contains rich seams of fool's gold, or iron pyrites, iron sulfide. Gold extraction is far simpler. To release the gold from quartz, one merely needs to crush the rock, freeing the fine grains of gold from the crystal structure. The rock dust can then be washed away, revealing the gold, which melts at a relatively low temperature. Panning for gold is a technique that mimics this process, though erosion has done much of the hard work by grinding the ore up over time. Gold was rare in the British Isles. 2,000 years ago, there were perhaps only 4 other locations where mining occurred: around Dolgelly in North Wales, the River Carnon in Cornwall, and in the rivers of Wicklow and Waterford in Ireland. When the Romans invaded Britain in 43 CE, they sought to exploit its mineral wealth. However, it would take over 30 years before they subdued the local Celtic tribe, the Siluri, and took control of the mining operations at Dolgelly. An interesting figure in this period was Julius Frontinus, who became the governor of Britain in 73 CE. Frontinus was not only a military general, but also an engineer with expertise in aqueducts. This skill was crucial for the Romans' mining operations. After gaining control of the mines, the Romans not only tunnelled into the hills using slave labour, but also built one of the longest aqueduct systems in Britain, an impressive 11 kilometres of leats and aqueducts. These channels delivered water to tanks at the top of the hill, and these could create floods that washed away the soil and exposed the seams of quartz in a method known as hydraulic mining. The Romans industrialised gold mining. Workers crushed the rock, and there's evidence that water-powered hammers also being used. They also devised a faster method of panning by using sluices to efficiently separate gold from the rock. This extraordinary, almost alien landscape in northern Spain, Las Médulas, once part of the Roman province of Hispania Tarraconensis. It was the largest open-cast mining in the entire Roman Empire. And what you see today is a landscape shaped by human hands. The geology here differs from that of Dolgelly, where ancient 450 million-year-old Silurian Ordovician mudstone holds gold-bearing quartz. At Las Médulas, the landscape consists of Neogene alluvian conglomerates. These are sediments deposited over the last 20 million years by great rivers that wash down material from eroded mountains, which once held the seams of gold. Between 23 and 150 CE, the area was the largest gold mining operation in the Roman Empire, employing tens of thousands of forced and free labourers. According to Pliny, the elder who served as procreator, the mine produced an astonishing 5 tons of gold a year, amounting to roughly 1,500 tons over the entire lifetime of the mine. The Romans employed hydraulic mining here on a grand scale, using water to tunnel into the hills. They exposed the gold deposit buried within ancient riverbeds, laying bare the riches hidden beneath the surface. In the Roman period, gold had evolved beyond its role as a decorative metal, symbolizing artistry and power. It had become a cornerstone of civilized life, currency. The use of money as a convenient form of barter first emerged in China around 2,600 years ago, with the Greeks adopting the idea soon after. It was a radical step in human civilization because it standardized value, enabling easy trade across large distances and laying the foundation for more complex financial systems and economies. Rome embraced coinage around 300 BCE, with its first mint located next to the temple of the goddess Juno Monata, from which we derive the words mint and money. For Rome, coinage was essential. It paid the wages of the military, an army that, if unpaid, could easily be swayed to join their commander in a coup to seize Rome. The Romans also introduced the revolutionary practice of featuring the head of the ruler on the coins, with Julius Caesar being the first to do so. This not only solidified the emperor's authority, but it also served as a powerful reminder to even the most distant parts of the empire who was in charge. Money sustained Roman elites and it powered a vast economy. While the Roman minted coins in bronze and silver, gold was the standard of value. This reliance on gold was so significant that when the economy began to falter in the 3rd century, emperors resorted to debasing gold coins with cheaper metals like copper to maintain the currency supply. Gold's role extended beyond Rome, becoming the foundation of the modern economy, the gold standard, which has only recently been abandoned. And that once provided a universal measure of value, stabilizing global trade and finances. A practice invented by the Romans for refining gold, and still used today despite its dangers, involves adding mercury to the slurry of gold-bearing rock to extract the pure gold. Mercury is found in cinnabar, a quartz-like mineral that was initially valued for its brilliant red pigment. As mercury sulfide, it can be easily smelted, yielding liquid mercury, also known as quicksilver. The Romans quickly discovered its toxic nature, as prolonged exposure caused symptoms like trembling, madness, and death. Aware of these dangers, the Romans chose to exploit it, often condemning criminals to mine and refine it. When mercury is added to gold ore, the slurry, the mercury forms an amalgam with the gold through a process called amalgamation. This is not a creation of a new mineral, but rather a physical process in which the mercury dissolves the gold, effectively separating it from the crushed rock. Now, cinnabar, as both a source of sulfur and mercury, played a role in the development of alchemy. The belief that base metals like lead could be transmuted into gold, which included getting the right composition of mercury and sulfur in the formula. Johann Friedrich Bottier was born 1682, the son of a local master of the mint, and from a young age Johann displayed a remarkable scientific talent and sought to make his fortune by unlocking the secrets of alchemy. Bottier's reputation as a gifted alchemist attracted the attention of powerful rulers, so much so that King Frederick I of Prussia had him taken into protective custody to work in the royal laboratory here in Dresden. After a brief escape, Bottier was recaptured and brought back to Dresden, where Augustus II, the monarch of Saxony, who was equally obsessed with gold and in dire needs of funds, imprisoned him to work on Goldmachentincture, a potion that could supposedly create gold. Alchemy, which combined elements of spirituality, chemistry, pharmacy, and metallurgy, had been practiced since the time of the Greek philosophers. The word alchemy derives from chem, the ancient name for Egypt, leading to its association as the science of the Egyptians, hence chemistry. Though steeped in mysticism, alchemy remained a respectable field of research until the early 19th century. Alchemists believed that all matter was composed of the 4 elements: earth, air, fire, and water. Gold, in their view, was the purest form of metal, the purest form of earth, while other metals were seen as impure. Since cinnabar could purify gold, many alchemists theorized that with the right combination of mercury and sulfur, other metals could be transmuted into gold. Alongside these pursuits, alchemists also sought a formula for eternal youth, and went slightly crazy. For 2 years, Bottier toiled, unsurprisingly without success. Augustus then appointed scientist Arnfried Wolfer von Chillenhaus to oversee the young alchemist. After 3 more years of fruitless efforts, Bottier, fearing for his life, turned his focus to von Chillenhaus's side project, creating white gold, better known as porcelain. At the time, porcelain was a highly prized export from China, and European nobility spent vast sums, mainly in gold, to acquire it. A fine clay called kaolin could be found across Europe. The exact formula for porcelain was a closely guarded secret. In 1708, working in a newly outfitted laboratory here in Dresden, Böttcher and von Schullenhaus made the breakthrough. They discovered that quartz, the very waste product of gold mining, was the vital ingredient in producing porcelain. And at the age of 28, Böttcher's fortunes changed. He was appointed to lead the first European porcelain factory, and it was a venture that would bring great wealth to Saxony. Though his pursuit of gold had failed, the white gold of porcelain proved to be just as valuable. Poor old Johann. Rich, but he never got a statue. He did make the town stinking rich. "40 kilometres east of Johann Böttcher's birthplace lies the unremarkable town of Glockha. It was, however, the birthplace of the remarkable scientist Georgius Agricola, born a century earlier in 1494. Originally named George Bauer, meaning farmer, he changed his name to the Latinized Agricola to align with his scientific ambitions. The pursuit of gold had driven the development of chemistry and mineralogy, and it also laid the foundations of our modern understanding of geology. Although Agricola began his career in an era dominated by alchemy, he moved beyond its mystical elements, focusing instead on mining and the refining process. To the south of Glockha lie the Ore Mountains. These straddle the German and Czech border, and it's a rich region in mineral deposits. And it was here that Agricola developed his scientific understanding. Disappointingly, they are not mountains but lower hills. But it is here that dwarves emerged into human consciousness, and supernatural beings renowned for their mining and craftsmanship, and evidently small enough for the mine tunnels, and who may have considered these hills to be bigger. In his early work on natural fossils, Agricola sought to classify minerals, sediments and rocks, and embarked on a lifelong journey to create a comprehensive understanding of geology. By the time of his death in 1556, he had completed his seminal work, the Re Metallica, which became the cornerstone of mineralogy and mining sciences. These mountains allowed Agricola to make remarkable observations about the formation of ores. He noticed that valuable minerals such as silver and copper were often found in fissures or veins within the rock, and these veins were frequently filled with a different type of rock or mineral than the surrounding material. This led Agricola to conclude that the minerals had been introduced into the veins rather than being part of the original rock formation. Agricola also observed that these mineral veins followed specific patterns and were particularly found in particular types of geological formations, indicating that their distribution was not random. He correctly deduced that ores were accompanied by impurities, or secondary materials, which suggested that metals were carried into the rock by external forces. A significant insight came from his studies of caves and mineral deposits, which often appeared in layers. Agricola proposed that hot thermal fluids from deep within the earth were responsible for transporting valuable metals dissolved in water. These fluids forced their way into the cracks in the rock, depositing minerals as they cooled, and his observations were largely correct, and laid the groundwork for modern understanding of hydrothermal ore deposits. So, hard to believe, but this was once hot fluid, pushed up through ancient siltstone, and then crystallizing out as hard quartz. In 1696, Sir Isaac Newton, then aged 56, took over the Royal Mint and the Tower of London, tasked with tackling widespread counterfeiting and coin clipping, a practice where small bits of coin were shaved off. Newton set about creating a more stable and reliable currency. This was just one of the many aspects of his multifaceted life. However, for our story, it's his fascination with the sun and astronomy that takes centre stage. Newton's interest in the sun began early. In his 20s, it is said that he blinded himself for 3 days after attempting to study the sun using a mirror, a testament to his intense curiosity and determination. Fortunately, he recovered, and his exploration of light would go on to revolutionise science. Newton's work with glass prisms, now they were a common curiosity at the time, led to one of his most famous discoveries, the true nature of light. In 1704, he published his groundbreaking treatise, Optics, in which he analysed the fundamental properties of light. By shining light through a prism, Newton demonstrated that white light is actually composed of a spectrum of colours, the familiar rainbow. It was Newton who coined the term spectrum to describe this band of colours. While many ancient cultures, such as the Egyptians and the Mayans, associated gold with the sun and believed it was a manifestation of the sun's power, Newton's work showed that the sun's light is actually white, not golden. This insight laid the groundwork for much of modern optics. Newton's fascination with light was driven by his passion for astronomy. At the time, lenses and telescopes distorted magnified images, so Newton invented the reflecting telescope to reduce these distortions. Whilst it wasn't perfect due to the limitations of mirror making at the time, his invention solved many issues associated with traditional refracting telescopes. Newton's contribution to the understanding of sunlight and optics, particularly his discovery that light can be separated into a spectrum, remains a foundation in both physics and astronomy. And our next step in the human understanding of the cosmic origins of gold come from a young Joseph von Fraunhofer of Bavaria. At the age of 19, in 1806, he began his apprenticeship at a secularized Benedictine monastery, renowned for its glassmaking. While his family had a long history in the craft, it was Joseph's innovation in glass quality that addressed the limitations of scientific lenses, which had previously hindered Isaac Newton. With improved lenses and telescopes, Fraunhofer revisited Newton's studies on the spectrum of sunlight. His enhanced instruments allowed him to observe the spectrum with greater clarity and identify dark absorption lines, known as Fraunhofer lines. And this marked a significant advancement in spectroscopy. Fraunhofer's work extended beyond the Sun. He also mapped absorption lines in other stars, including Sirius, the brightest star in the night sky, and noted variations in the patterns, further developing the field of spectroscopy. This is Göttingen University, hometown of George Bunsen, patron saint for all school kids to setting fire to things. Göttingen University, where some of the greatest minds in science have walked. One of them, Robert Bunsen, became a legend for his contributions to chemistry. And yes, he's the reason we have the Bunsen burner. But Bunsen's real genius was in using heat to unlock the hidden signature of elements, leading to the creation of spectroscopy, a method extensively used today to analyze everything from the air we breathe to the stars in the sky. His method involves heating various substances and observing the light they emit. The spectrum produced reveals distinct fingerprints of each element. If I take a thin strip of copper and place it in a burner, you can see it glow. By exciting the atoms, it emits light that can be analysed as a spectrum. When viewed this way, the spectrum looks like a barcode, with dark lines representing areas where the element absorbs light. This pattern allows us to determine the composition of any excited materials. While I don't have gold to burn, its spectrum would have a similar barcode-like appearance. Bunsen used this technique to discover two new elements, cesium in 1860 and rubidium in 1861. His work extended to gases and photochemistry as well, broadening the reach of spectroscopy. In the decades since Bunsen's pioneering work, the sciences allow scientists to study not only earthly elements, but also the compositions of our nearest star, the Sun. This solar spectrum, far more detailed than anything Newton could have imagined, reveals dark absorption lines that indicate which elements and in what proportions make up the Sun's composition. Dr. Celia Payne Gaboshkin, born Cecilia Payne in Wendover, Buckinghamshire in 1900, stands as one of the most significant yet often overlooked figures in the field of astronomy. At the age of 25, her doctoral thesis revolutionized our understanding of the stars. She proposed the stars were composed primarily of hydrogen and helium, contrary to the prevailing belief that stars were made up of the same heavy elements as Earth, such as iron, silicon and carbon. Before Payne's research, scientists believed that stars had a similar composition to the Earth's crust, but the observed spectral lines did not match the expected amounts of these elements. Hydrogen, for instance, appeared to be far more prominent than heavier elements, which posed a problem. Payne's insight was that the temperature of the star affected the visibility of certain elements in the spectra, leading to an overestimation of heavier elements. Her elegant solution, adjusting for temperature, allowed for an accurate understanding of stellar compositions, demonstrating that hydrogen and helium were the most abundant element in the stars. Why have we not built statues to this woman? Today, tools like NASA's Hubble Space Telescope can peer into distant gas clouds and witness the very stardust that makes up our universe. A few billion years after the universe's birth, the first stars, gigantic up to 1,000 times the size of our Sun, were formed from hydrogen. These massive stars lived fast, burned out quickly, and died young, existing for just a few 100 million years. Inside their hot cores, hydrogen was fused into heavy elements like oxygen, silicon, and carbon, producing the first 26 elements of the periodic table, up to iron. When these stars exploded in supernovae, they scattered these elements across space, forming immense gas and dust clouds. To create elements heavier than iron, more energy is required. Energy that could only come from rare and violent cosmic events. Gold, for example, forms when neutron stars collide, releasing a payload of precious metals in the resulting explosion. Amid one such cosmic dust and gas cloud, our solar system was born around 4.6 billion years ago. Alongside our Sun, other stars like Alpha Centauri and Proxima Centauri emerged. In a stellar nursery similar to the one that birthed our solar system, we can see the formation of new stars today in the Orion Nebula, also known as M42, appearing as a faint smudge to the naked eye. This nebula is actually a vast dust cloud many light years across, containing hundreds of potential stars and even protoplanetary systems. These spinning disks of dust and gas follow a familiar pattern. Hot hydrogen and helium at the core, rockier elements forming closer to the centre, and bands of gas and ice further out, much like the gas and ice giants in our own solar system. As gravity pulls the core inward, nuclear fusion ignites, leading to the birth of new stars and planetary systems, just as it did for us billions of years ago.
Gold is literally astronomically rare. If you imagine this, all this sand in this bucket, it's about 150 million grains of sand. It's all the mass in our solar system. Then 99% of it is hydrogen and helium, mainly locked up in the Sun and the gas giants. 99%, that's hydrogen, 75%, 25% helium. That, 150 grams, is all of the heavier elements, everything above helium. And this one tiny grain of sand, which you obviously can't see, is all the gold in our solar system. To have it being a whole grain, you would need 10 big builders' dumpy bags of sand.
Earth, being a rocky planet, mainly consists of the heavy elements. Almost half the Earth's crust is oxygen, with silicon next, followed by metals, and the last 1% are all the other elements. If all the earthy elements were represented by the sand in my bucket, then all the gold in the crust would be about 6 grains. That's still about 35 million tons locked away in the crust. Humans have mined about 200,000 tons in all of history. Now, divided up equally amongst everybody, we would get about 25 grams of gold each. That's about 5 rings worth. It's Earth's liquid oceans and its active tectonic surface that it's the next step in how this rare stardust ends up as a ring on your finger. There's actually much more gold on Earth, in places we haven't been able to access yet. Take the oceans, for instance. A cubic kilometre of seawater holds around 26 million tonnes of salt. About 2/3 of this is chlorine, most of the rest is sodium, and the remainder contains metals like aluminium, potassium and calcium. In that cubic kilometre of seawater, there's also about 13 tonnes of gold. But the challenge lies in how to extract it. Gold in seawater is present mostly as a dissolved ion or complex, an atom floating around in the water. And as yet, we haven't discovered a cost-effective way to extract it from the ocean. Now, water is the booze of our planetary party. It's an excellent solvent that allows elements to mingle. But to really kick off a party, and to get some serious mingling, we need a dance track. The heat from Earth's molten mantle. This heat gets elements moving, concentrating them in rich deposits over geological time. Gold began its earthly journey on an ancient seabed, near a hotspot like the Atlantic Ridge, where seawater seeped into the seabed's cracked, was heated by geothermal forces and the dissolved minerals as it circulated. These hydrothermal fluids were then pushed back to the seabed, spewing rich minerals from vents similar to an underwater geyser. Now, this process, repeated over millennia and millennia, slowly concentrates metals like gold. Eventually, plate tectonics push these ancient mineral-rich seafloors deep underground. Now, if you take Spain's Iberian pyrite belt, once part of the African continent, it was subducted under the Iberian plate. Now, as mountains rose, volcanic activity drove water rich in metals back up through the ancient seabeds, and this concentrated ores like copper near the surface, hence the large copper mines in southern Spain. Welsh gold had a similar story. 500 million years ago, the ancient Iapetus Ocean. Iapetus was the father of Atlas, hence the Proto-Atlantic Ocean, off a small continent called Avalonia, lay just south of the equator. This seabed was later forced into the Caledonian mountain range as Avalonia collided with a continent carrying what we now call Scotland, America and Scandinavia. During this immense upheaval, mineral-rich fluids heated, pressurized by tectonic activity, pushed up through the sedimentary rocks of South Wales, bringing with them metals like lead, silver and copper, and of course gold. Gold, unlike other metals, well, she's a bit posh. While elements like iron, copper and lead are content to party with little heat, and sulfur, forming very stable compounds, stable relationships, gold, well, she remains aloof. It's only occasionally she'll pair up with chlorine in hot geothermal fluids. The booze really needs to be flowing, and the party needs to be swinging. As the fluid cools and the heat dissipates and the party ends, gold separates from chlorine, completely no memory of the event, precipitating out in its pure form, often locked in with quartz, silicon dioxide crystals. So, a tiny piece of gold in your wedding ring has travelled across space and time, forged in ancient stars, refined through Earth's geological processes, a precious and rare and treasure of the universe. Gold has captured the hearts, minds, and desires for humans for millennia. It has driven people to madness, inspired the creation of beautiful objects, and pushed us to explore the Earth and beyond. Its allure lies not only in its rarity, but in its exceptional properties. Gold stands apart from other elements. It doesn't react with them, it doesn't tarnish, and it light shimmers in a way that's uniquely its own. This beauty stems from gold's atomic structure. We can't see the frenzied movement of its electrons as they roam freely within an ordered lattice of gold atoms. But this sea of electrons, as it's called, reflects light in a truly remarkable way. Unlike metals that oxidize, or non-metals with rough, uneven surfaces that scatter light, gold is like a calm surface of a rippling ocean at sunset, reflecting light in a golden glow. The alchemists viewed gold as the purest form of Earth itself. And even now, with the benefit of modern science, gold retains an almost magical property, making it one of the most prized and enduring substances in the world. Gold represents order and beauty in the universe, and perhaps as stardust ourselves, we are drawn to that order. We, as conscious beings, are part of the universe, and as such, we can appreciate the extraordinary beauty of gold, its permanence, its shimmer, and the cosmic journey it took to become the ring on your finger. So I really hope you enjoyed this video. Do like, comment, and subscribe. Thank you.